In this video we're going to be talking about acids, bases, pH, oxides and acid rain. Simple definition of an acid: it's a substance that produces hydrogen ions, actually hydronium ions, we'll talk about that in a second, when in solution, so when it's dissolved in water. So you may well have seen a reaction something along these lines. So we've got the dissociation of nitric acid to give a proton, an H+ ion, and a nitrate ion. This is probably how you've been presented it with before, and it is a simplification, because what is actually occurring, we've got a reaction of nitric acid, liquid nitric acid, with water, and it produces this thing called a hydronium ion, so H3O+, and a nitrate ion. So it's not this, it is H3O+, is actually what's happening in real life. Another example is for hydrochloric acid. We've got hydrochloric acid dissociating to give a proton and a chloride ion. When in real life it is a reaction with water to produce the hydronium ion and chloride ions. So once again, acid being a substance that produces hydrogen ions, hydronium ions in solution, and that's what an acid is. Some common acids which I am sure that you are used to or you have seen before. We've got hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid, HNO3, acetic acid, CH3COOH, which you find in vinegar, and we've got carbonic acid, of which we will talk about more in a following video. Some basic properties of acids: they taste sour. So you grab yourself a lemon and have a bit of a bite, then the sour taste is from the citric acid that's in that lemon. Acids react with many metals, for example zinc and magnesium, to form hydrogen gas. You've probably all performed the POP test in your science days. Acids attack limestone and the metamorphic rock of limestone, which is marble. They are both attacked by acids. We'll come to that later as well. They sting or burn the skin, and they turn blue litmus red, as shown in these particular photographs. Simple definition of a base. A base is a substance that contains the oxide ion or the hydroxide ion, or which produces hydroxide ions in solution. So a soluble base is called an alkali. So sodium hydroxide is soluble in water, so it's a base because it's got hydroxide, and it's also an alkali because it is soluble in water. Now we've also got this little step here, or which produces hydroxide ions in solution. So for example, if I've got ammonia, which happens to be a base, it reacts with water to produce ammonium hydroxide. And because it's producing ammonium hydroxide here is shown dissociated, it is classed as a base. Now we've also got sodium hydrogen carbonate, so sodium bicarb, reacting with water to produce carbonic acid, and once again sodium hydroxide. Now sodium hydroxide here again, it's written dissociated, but showing how sodium carbonate is reacting as a base because it produces hydroxide ions. Some common bases, some of these you will have heard of before: sodium hydroxide, sodium NaOH, and calcium hydroxide. Calcium hydroxide is lime water, so a solution of calcium hydroxide is lime water, which you've used, I'm certain for detecting carbon dioxide gas. Carbon dioxide turns calcium hydroxide solution cloudy, because we've got the formation of calcium carbonate. We've got sodium oxide, sodium hydrogen carbonate, so sodium bicarb, find it in your kitchen. And we've got ammonia. Ammonia is found in lots of cleaners, for example window cleaners and things like that. Some properties of bases: they taste bitter. They feel soapy. So if you're using some sodium hydroxide and you start feeling your fingers and they're slippery, it's almost certainly you've got some sodium hydroxide on it. It is time to wash your hands. They react with fats, and they react with fats in a way that is used to make soap, which we'll examine at a later stage. And they turn red litmus paper blue, or red litmus indicator blue. In this case we've got red litmus going to give blue litmus when a base is added. Okay, the pH scale, which if you have a fish tank or a swimming pool, you may well have been using. We have got, scale goes from 0 to 14. Actually 0 is incorrect because we can actually go into negative numbers. If we look at something with a pH of 7, it is neutral. And it's actually worthwhile saying that all substances are either neutral, or they're acid, or they're basic. So up the top here we have got acids, and down the bottom we have bases in this particular scale, this particular diagram. So we've got acids and bases. For example, some just common ones, we've got battery acid as being a really strong acid. We've got tomato juice being a much weaker acid. So the further away they are from neutral, the stronger they are. So something with a pH of 0 or less is a very strong acid. Something with a pH of about 6 is a very weak acid. Same with bases. If I go just pretty much not very far away from neutral, it's a weak base. So sodium carbonate is a weak base. If we go up to something which is far away from neutral, and we've got a strong base. Now we can't talk about the pH scale without talking about indicators. Now indicators are chemicals that change colour depending on whether they are in acid or basic solution. So some common ones, we've got litmus. Litmus changes from red to blue. So it's blue in base, red in acid, and it changes colour around about neutral. So around about pH 7 is where litmus changes. Phenolphthalein is another indicator, a common indicator. It goes from colourless up through a pretty pink, and it's quite an intense pink depending on how basic it is. It changes in the basic range, so it's changing around about pH 9. Methyl orange goes from a pink to a sort of a orangey yellow, and it changes colour in the acidic range, so it's changing around about pH 3 to 4. And we've got bromothymol blue, which goes from yellow to blue, and it's also, like litmus, changing pretty much around the neutral range. Any two of these indicators can be used to give you a rough indication of the pH of a substance. So if a substance is sort of yellow in methyl orange and yellow in bromothymol blue, that means it's got a pH roughly around 5. If you've got another substance which is colourless in phenolphthalein and blue in litmus, then it's pretty much around about pH 8. But if we've got a substance which is colourless in phenolphthalein, well, it's colourless in phenolphthalein anywhere from being a strong acid to being a weak base. So phenolphthalein actually will not tell us whether we've got an acid or a base. We'd have to couple it with another indicator to give us an indication. It's pretty remarkable what you can make an indicator out of. Now this is a table which has a whole stack of different fruits and skins and goodness knows what, which can be used to make indicator. Now in the classroom you may well have used red cabbage to produce an indicator, and it makes an actually startlingly good indicator as shown in the next slide. This is red cabbage indicator in different solutions. So it's sort of this pale blue in straight neutral water. We go to a weak base and it's lovely green. Go to a strong base and it's yellow. If we go to a weak acid, it's a sort of a pale pink. And hydrochloric acid, which is a strong acid, we're talking about it going to a much deeper colour pink. Cabbage indicator is produced just by boiling up some red cabbage and getting the resulting solution and adding a few drops of that to your acid base or neutral substance. Some everyday uses of indicators. So soil pH, if you want to have hydrangeas, well, the colour of the hydrangeas range from blue to pink depending on the acidity. Grass grows best in a fairly acid soil, so if you want to have a lovely lawn, you want to make sure your soil in which you want your grass to grow is fairly acidic. Swimming pools, you don't want it too basic or too acidic. And fish tanks. Fish have specific pH ranges in which they are happy, so you need to make sure that your fish tank stays at the right pH. Testing the pH of soil is fairly easy. You get some barium sulfate, which is actually a powder, and you just puff some of the powder on the soil that you want to test the pH of, and then you put a drop or two of universal indicator, and the universal indicator changes the colour of the barium sulfate, or the barium sulfate now enables the colour of the universal indicator to be evident, and for this case you're probably looking at about a pH 6, so that is slightly acidic soil. An astonishing amount of substances exist as oxides, so combined with oxygen. Now because we're talking about the acidic environment, we're talking about the pH of oxides. Okay, so we're talking about the acidity of oxides, and basic oxides are metal oxides. So the vast majority of metals, when they are combined with oxygen, form bases. Okay, amphoteric oxides are oxides that can react with both acids and bases. And if we're talking about the non-metals normally make acidic oxides, and the noble gases form no oxides at all because they don't form compounds at all. Acidic oxides are oxides that react with water to produce an acid, or react with a base to produce a salt and water. So these examples here, we've got nitrogen dioxide reacting with water to produce nitric and nitrous acid. We've got sulfur dioxide reacting with water to produce sulfurous acid. That's not sulfuric acid, it's sulfurous acid. So SO3 means it's sulfurous. We've also got carbon dioxide reacting with water to produce carbonic acid. So those are all examples of oxides reacting with water to produce an acid. The other example is when an oxide reacts with a base to produce water and a salt. Now this is just the salt sodium carbonate, which has been written in an ionized or a dissociated way. Another example of that is we've got phosphorus pentoxide reacting with sodium hydroxide, producing the salt sodium phosphate and water. So both of these examples are showing how acidic oxides can react with a base, both cases sodium hydroxide, to produce a salt and water. We're not going to spend much time on basic oxides. Basic oxides are oxides that react with an acid to produce a salt and water. In this case, we've got copper oxide reacting with sulfuric acid, giving copper sulfate and water. Amphoteric oxides. Amphoteric oxides can react with both acids and bases. So for example, I've got zinc oxide here reacting with hydrochloric acid to produce zinc chloride and water. And in this case, it's just showing like a generic acid, so it's just H+, and we've got zinc ions being produced. So this top reaction here does not have the chloride ion spectator. The chloride ion here in this reaction is a spectator because it is unchanged in the reaction. Everything else is changed, so this is just a net ionic equation for that particular reaction. So that's zinc reacting with an acid. This one, the next one, we have got zinc reacting with a base. So in this case, we've got zinc oxide again, but it's reacting with sodium hydroxide and water, and it's in this case, it's producing sodium zincate. Now, this particular ion here is called the zincate ion. And once again, this top reaction here, that is just a net ionic equation for this one, and we're just not including the sodium spectator ions. So once again, we've got zinc oxide reacting with hydroxide to give the zincate ion, and this reaction does not include the sodium ions, which are spectators. So amphoteric oxides react with both acids and bases. There are a couple of acidic oxides that we're going to spend a bit more time on. The first of those is sulfur dioxide. Now, sulfur dioxide is released naturally where we've got hot springs and in volcanoes. So this hot spring is actually showing the elemental sulfur, that's that yellow stuff. And the yellow stuff here is also elemental sulfur, but both hot springs and volcanoes release sulfur dioxide directly into the air. The elemental sulfur found around hot springs and volcanoes is actually produced by the reaction of sulfur dioxide released by the volcano and hydrogen sulfide also released by the volcano or the hot spring, and those two react to produce elemental sulfur, which is found around these places. Humans release lots of sulfur dioxide into the atmosphere, so mainly through the combustion of things like coal and also in smelting. But if I've got some coal, so this is a nice pretty picture of coal, thank you Wikipedia, it contains some iron pyrite, and when it is combusted it produces iron oxide and sulfur dioxide, that which is released into the atmosphere. So for example, if I've got sulfur in the compound reacting with oxygen to produce sulfur dioxide, that's just like a generic equation for what's happening. This is a specific example that's used for when we've got the combustion of coal, because again the coal contains some iron pyrite. Just for interest's sake, iron pyrite is called fool's gold. Now here's a picture of some fool's gold. We've also got when zinc is being produced, zinc mainly is found as zinc sulfide. One of the first steps in its smelting, or in its production, is a reaction with oxygen to produce zinc oxide, and that also releases sulfur dioxide. The other oxides that we're going to be looking at are the oxides of nitrogen. We've got a pretty picture showing some lightning here. Lightning has enough energy to overcome the activation energy requirements of this particular reaction. So we've got oxygen reacting with nitrogen, producing nitric oxide. Now that occurs naturally when we have lightning. The nitric oxide then reacts with oxygen to produce nitrogen dioxide. Now nitrogen dioxide is acidic, whereas nitric oxide is not. So again, naturally that's occurring when we have lightning. From human sources, these reactions, or this reaction in particular, occurs in internal combustion engines, in power plants, etc. Again, when we're in an internal combustion engine, we have got rather extreme conditions and lots of heat, and that is enough to overcome the activation energy requirements for this particular reaction. So human sources, internal combustion engines, natural sources, things like lightning. The Industrial Revolution led to huge amounts of sulfur dioxide being released into the air. Sulfur dioxide is an irritant of the respiratory system and led to some truly spectacular smogs, culminating in the Great Smog of 1952 in London, which directly led to the death of 4,000 people, and overall about 100,000 people were adversely affected. Nitric oxide and NO and nitrogen dioxide, NO2, which are collectively known as NOx, along with hydrocarbons released by motor vehicles with the action of sunlight, led to the production of ozone, which is also a respiratory system irritant, and this mix of chemicals is called photochemical smog. Now you'd think that there'd be a great increase in SO2 and NOx in the atmosphere over time, due to our increase in both the burning of coal, which contains sulfur dioxide, or contains sulfur which is turned into sulfur dioxide, and the production of NOx through greater use of internal combustion engines in cars. However, there is no direct evidence of increased global concentrations of these gases. The instruments needed to measure the small concentrations of these gases, and we are looking at concentrations around 0.01 parts per million, have only been available in the last few decades. Localised increases in concentrations have been measured around cities. However, there is strong indirect evidence by way of the acid rain that is produced by these gases that the concentrations have increased. The effects of acid rain are measurable and can be compared to the past, and no such effects had been previously recorded. The actual formation of acid rain: sulfur dioxide reacts with water to produce sulfurous acid, and then the sulfurous acid reacts with water to produce sulfuric acid. Nitrogen dioxide reacts with water to produce nitrous acid and nitric acid. And both of these are effectively washing the sulfur dioxide and the nitrogen dioxide out of the atmosphere. Hence, their actual concentrations in the atmosphere haven't increased, but that doesn't mean it's not released and then precipitated as acid rain. Acid rain causes a multitude of different bad effects. A few of them are listed here. So we've got acid rain leaches toxic chemicals such as aluminium from the soil, which runs into streams. Now, aluminium is directly toxic to fish. Okay, it's also toxic to plants if it builds up. It dissolves helpful minerals such as calcium and magnesium and removes them before they can be used by plants. Essential nutrients in leaves are stripped away by acid rain, making the tree more susceptible to damage by other environmental factors such as cold weather. Low pH is directly toxic to fish. At pH 5, most marine eggs won't hatch. So we're talking about eggs being made out of calcium carbonate, and if we've got acidic water reacting with the calcium carbonate, which means we've got very weak eggs. Metals such as bronze are corroded, so if we're talking about historic statues and things like that are being damaged by acid rain. Paint is damaged by acid rain, and stone, particularly things like limestone or marble, are literally eaten away, are deteriorated by acid rain.